She is, yeah.
Prove set theory and logic. Today we're going to prove that this is set theory and logic. No, I'm just kidding. Let's get into it. So it's Monday. We're talking about complements.
Yeah.
It's a great Monday. Complement the day, yeah. So we're talking about complements today, if you recall. A couple of things before we start talking about complements, though. Next time will be our review session before the big exam on Friday. The exam on Friday, by the way, for everyone in here, I will have someone else proctoring it. So, easiest day to miss is the day that you have to proctor. I will be out of town. I'm going to be in South Dakota officiating my sister's wedding. I got ordained as a priest, technically online. So I'm going to do my first wedding. It'll be fun. Weird, right? But yeah, so I will be out of town for the exam, but as you sit in silence, I guess you'll have to look at someone else's smiling face up here. Hopefully it should be pretty straightforward though. So bring your questions for next time. Things on the exam to know. We'll talk about this next time too, but just to head off the emails I always get. Yes, you can have a calculator. No, you can't have one of like those really fancy new ones that are basically just phones and have like internet connections and everything, right? I've seen people try to sneak those. No, you can't use your phone as a calculator. I'm not stupid. But yeah, you can have calculators. You can use whatever pens you want. Just don't write in red pen. No, it's not open book. Is it hard? Maybe. Depends how much you study. How long is it? I'm not going to tell you. It's not too long. There we go. So that's like the standard list of questions that I always get on every exam. All of the more specific questions about the material, please bring with you next time. We will answer all your questions and get into it. If you recall also, the next homework is due on Wednesday, and the key will go live then. So I encourage you to complete it and look over the key, and also look over the key for the first assignment. Check your answers against it. If you want feedback on your assignment, please also let me know. You can just, in your submission online, it's got like a comment box where you can type stuff, right? You can just say comments, or give me feedback, or email me and say, I want feedback. And then I'll go annotate and mark up your document. Cool? Cool. Right on. All right, so complements. Last time we were talking about complements. So recall the relative complement of B in A, also called the set difference, is the set A set minus B, which is the set of A such that A is in A and A is not in B. In a given universe U, we may also define the complement of a set A to B. Either we write it as, say, like A prime, or if that looks kind of confusing, occasionally I'll write it as AC for complement. And either way, what it is, it's the set of, I'll write it this way, it's U set minus A. That is, it is all of the things in the universal set that are not in A. So you can take the complement of a set relative to another set, and if you're working with a universal set, you could just talk about the complement quite generically. Visualizing this is all actually kind of nice and easy to visualize. We've got our Venn diagrams that we've been doing. Ooh. Let me double check and make extra sure. Okay, good. I did press record, and I am on the right camera. All right. I wanted to make sure I did not forget to do that. I don't want to have to re-record this. So we've had our nice Venn diagrams here with A and B. We have A union B. This goes all around both of them, just to recall. This is A union B. Then we have A intersect B. That's right in the middle. And then there are the other two possibilities we could have, which I will write in different colors now. There is A without B. That would be over here, but not in there. This is A set minus B, the relative complement of B and A. Yeah? And then you have the other one, which is on the other side, and now I have too many markers in my hands. All right, you have the other one on the other side, which just goes like right over here. And this here is B set minus, oh, did my slash the wrong way, A. And then, if you want to think about it just relative to a single set, you could also just look at a set A, and then everything out here would be a complement. That is, supposing, of course, that everything out here is nebulously in some universal set U. Does that make sense? Sweet. All right. So if you think about it, we kind of covered all the different regions, right? If you've got two sets, you can be like, what's in both of them? What's in either of them? What's in one of them but not the other? Or what's outside of them? And that's the complement in the universal set. There's no regions left to cover. We've basically covered all the different ways you can put them together like this. Cool. All right, let's prove some facts about complements. A nice little theorem to begin the day with. This theorem is known as De Morgan's law. So what it says is, I'll write it this way, let A, B, and C be sets. Then the claim is as follows. 1, A set minus, not a set bracket, a parenthesis, B union C is equal to, well, A set minus B intersect A set minus C. And write that intersection symbol a little bit nicer. And then we've got the second counterpart. Can you imagine what it's going to be? It's going to be A set minus B intersect C. And what that is, can you guess what it'll be? The same pattern yet again, but perhaps this will flip from an intersection to a union. And there we go. So what does it say? It looks complicated at first. My gosh, what a little sea of symbols. Distribution. That is exactly it. It is exactly the same as what we were doing before. I have to make sure I don't keep walking out of frame. Basically what it says is, hey, look, you can take these and you can distribute it out. So you get A set minus B and A set minus C. But when it distributes across this little guy, it flips it. Kind of cool, huh? If you think about it for a second, this isn't that weird. What it says is that if you take A and you cut out the pieces that are in either B or C, that's the same as taking the pieces that are in A but not in B, and the pieces that are in A and not in C. That is, you say, okay, if you want to visualize it, here, maybe I'll kind of draw it. There's unfortunately kind of a number of different ways that this could go in terms of our Venn diagrams, right? Many different ways to have 3 circles overlap. But if you want to think of it in kind of a nice and easy way, so here I'll draw, see if I can draw this trio of circles well. There we go. If I've got A, I've got B, I've got C. Let's look at B union C. That would be this little weird shaped thing right there. And if I take A without B union C, well then that's just this little chunk right here. What the claim is that you can get here by taking A without B. So that would be everything in here. If this is hard to see, I'm apologizing for that. And then you could also do A without C. Actually, maybe I'll draw this off to the side to make it clearer. So here's the pieces. Okay, so A, B, C, A, B, C. You could take, instead, you could grab one chunk here, which is easier to shade. This is A set minus B. And then you could grab the other chunk here. This is A set minus C. And notice if you intersect them, then it's going to cut off these weird little corners right here. And those are precisely the corners that you want to be cut off to get A set minus B union C. Does that make sense? Okay. So if you just overlay these two shapes on each other, it would just cut off those two corners and you'd be left with that weird shape. Yeah? So De Morgan's laws perhaps make some sense, or at least the first of them does. What about the second one? It says A set minus B intersects C. Ah, well this would be a slightly different one. Notice, if it's A set minus B intersects C, well then in that case, we're going to have to draw B intersects C instead of B union C. And what that will look like is basically the same thing, just a little teeny tiny bit different. You've got A, you've got B, you've got C. If you look at B intersects C, it's this little region right here. Yeah? And if you go A without that, then what you want to pick up is everything except for that little chunk. See? Kind of Pac-Man looking shape. All right. And what it says is that you could first take out B, you could first take out C, and then you could look at the union of those two things. That is, for these drawings down in here, actually they're almost the same. A, B, and C, A, B. You've seen a professor just like really perfectly draw a circle on a whiteboard? What's up with that? I can't do that. I've been doing this for so many years and I cannot draw like, you see this professor just draw like that absolutely perfect circle just with no effort? That's weird. They should like be playing sports. They should, or like, you know, drafting the designs for buildings. They shouldn't be teaching. I can't draw for crap. All right, so if you take A without B, that gives you this chunk right here, kind of a half moon shape. If you take A without C, that gives you this chunk right here. And if you put them together, notice what you get from this piece and that piece. If you overlay them, you get back this Pac-Man shape. The only piece that gets missed is the piece that's in both of them, right? Oh, so that also makes sense. Look at this. You could do exactly what De Morgan did. You could draw some circles and back in the day make your claim to fame. But instead of drawing circles, let's prove this in a slightly nicer way. What do you think? Is this making sense? Everyone see in the picture? Feeling like you can reason visually about this? Yeah, right on. Okay. So let's try it. Actually, let's erase a little bit better, then let's try it. All right. Proof. Where would you start? What would you do? Well, let's start with number one. I think that's the easiest place to start. Okay, so let's say, hey, let's look at this. A, or I'll write it this way. I'll say, if X is in A without B union C, well, this happens if and only if X is in A and X is not in B union C. Since, after all, the set of A set minus B is the set of A's in A that are not in B. That is, A set minus B is defined via comprehension with this predicate. The predicate that is true when the thing is in A and it is not in B. So, an X is in A set minus B union C if and only if that X satisfies the predicate defining this set difference. And that predicate says, hey, is it in A And is it not in B union C? Okay, so what's an equivalence statement? Well, what we want to build to after some number of steps here is that X is in A set minus B and X is in A set minus C, right? It's in both of them. So notice this is not going to be too bad. This is true if and only if X is in A and not X is in B or X is in C. After all, the union is defined in terms of a predicate as well. It's a predicate which is true when you belong to each of the things. So if you're not in there, then not that predicate, right? Okay. Now, all we have to do is start hooking the pieces together. Okay, so this would still be X is in A. And now I'm going to distribute this not through the OR. Not X is in B and not X is in C. That is, if not a compound statement with an OR, then when I bring it through, you get not thing and not thing, right? Okay. So what can I do from here? Well, I could just rewrite this in a nice way. X in A and X not in B. And I'll write it this way, X not in C. Okay. Now I could perhaps do a little bit of distribution, right? And would this say something like X in A and X not in B and X in A and X not in C? Yes, though we are getting low on the board, so my apologies for that. But hey, would you look at it? Does this say X is in A and X is not in B? Well, wait a second. Something in A and something not in B. Set difference. What? There we go. Hey, cool. This if and only if X in A set minus B and X in A set minus C. But hey, what's the condition where something is in one set and something is in another set? Is that the predicate defining an intersection? Yes, right? Maybe? What are we thinking? That is, this here, I'm going to kind of go looping up so I don't go too low on the board, is true if and only if X is in A set minus B intersect A set minus C. And that's the statement that we want, right? That's not too bad, is it? Or is it? It certainly looks longer than maybe we perhaps first believed it would. That is, perhaps you prefer the picture drawing version. Yeah? It's understandable if so. It's easy to rely on your, I don't know what the right way to put it is. I would say like visual intuition, but I think perhaps like the right way of saying it is more like your sensory or like geometric information, right? Like you've got some sense that things basically work like the pictures of them, right? Like these kind of sketches you could make to sort of describe a thing, hopefully capture the properties of the thing well enough that your sketch allows you to reason about it. That is sometimes true, but occasionally it is not. So it is still very good, and actually the only technically correct way to get there, to go through the actual symbolic manipulation to derive the thing that your geometric or physical intuition about representations of objects leads you to. That is, we are reasoning about sets, not about circles on a whiteboard. You could certainly describe with these circles on the whiteboard some sets, perhaps the set of points within the circles, the region of the board enclosed by the circles. And certainly our reasoning seems appropriate when the sets involved are, parts of the whiteboard, right, enclosed by lines with markers. So it seems to at least hold for that type of set. But perhaps there are entirely pathological sets for which this sort of reasoning would not work. So for that, we must instead appeal to the actual definitions of these things to reason about it. That is, the visual proofs that people like to do are not, in, I guess, like a very technical sense, really correct. They only allow us to reason about certain types of sets, or via depictions of them. They are good to guide our intuition, but they are not enough. We need more. We need symbolic manipulation. Everyone's perhaps least favorite part of algebra, but perhaps one of the most important parts of math. Lots of hedging, saying perhaps a lot. All right, let's prove part number 2. So if we want to prove part number 2, can we go down basically the same chain of reasoning? Effectively, yes. And even better, since we're starting higher on the board, we can go through the same chain of reasoning and not run out of space and end up cramped at the bottom. So that's nice. All right, let's say, hey, what if x is in a set minus b intersect c? Well, this is true if and only if x satisfies the predicate defining this intersect, or this set minus right here, this relative complement. And what is that? Something is in a set, relative complement of that thing, the other set, if and only if it's in the first one and not in the second one. So that would be if and only if x is in A and x is not in B intersect C. All right. Well, what would this mean? Well, just looking back to before, all we have to do is say kind of the obvious thing. To be not in something means not the statement that you are in it. And then all we have to do is describe what it means to be in an intersection. Recall again that an intersection is defined in terms of a predicate. We are doing comprehension on a predicate. So this says x is in A and not, well, what do we need for x to be in B intersect C? Well, x has to be in both B and x has to be in C as well. So x is in B and x is in C. But hey, I know how to not a compound like that. X is in A, and now when I not this compound, what do I have to do? Well, I go not x is in B, or not x is in C, right? If the not of an and is ors, yes, exactly. All right, so from here we're pretty close. X is in A, and, well, I'm just going to turn these statements into x is not in B, or x is not in C. And if you look at what we want to get to, we are very, very close. We need only distribute. Yeah? Yeah. Hey, there we go. Excellent. So x is in A, and x is not in B, or x is in A, and x is not in C. But hey, each of these pieces here and here are the predicates of a relative complement. Yeah? So this is true if and only if x is in A set minus B, or x is in A set minus C, and something is in one thing or the other thing if it's in the union of those two things. That is, this is the predicate for a union. Oh, hey, how about that? So this says that x is in A set minus B union A set minus C. And we've shown what we want to show. We've reached the promised land of De Morgan's laws. Cool. Does it make sense, or does it not make sense? People are nodding and saying it makes sense. This is good. I hope the people listening in online also feel like it makes sense, since you can't say anything if it doesn't. Cool. Now it's time to talk about other ways that you can take sets and put them together to make new sets. So here's a thing to think about. So far, here's an idea, I guess, to consider. This is something that is not directly said in your notes, nor is it something that you need to know. But it's a good question to ask yourself. All of our sets are unordered, right? They have no intrinsic ordering of their elements, right? The set with the integers 1, 2, and 3 in it is the same as the set with the integer 2, 3, 1, right? Integers 2, 3, and 1. That is, sets are defined by what's in them, not what order they appear when we write them down. They're just a big old jumbled bag of stuff, right? Okay, how the heck could we encode ordering? That is, oftentimes we want to talk about ordering, something like, say, like an XY pair. You know, if you're thinking about plotting points on the plane, 1, 2 is not the same point as 2, 1. How on earth could we include an ordering in a set? How could we somehow describe this? In effect, if you think about it, it's kind of like arbitrary which way you pick to encode this. But if you pick a way to encode it, you could, you know, start to deal with these things in a reasonable way. But how would you pick to encode this? Does anyone have an idea? Think about it. If you have an ordered pair, so how could we encode an ordered pair as a set? Well, all we need is some set. All we need is a way to represent AB as a set so that AB is not the same as or is distinct from BA. Yeah? What could we do? What would you do? Do you have any idea of how to do it? I'm actually serious. Any real answers? What would you do?
Ordering relations. Like
well, you could define some kind of ordering relation, but just straight with sets. How would you, like, if you wanted to say, like, I'm just using sets to describe this concept, how could you encode it in a set?
two sets. Cartesian product.
Product? Okay, so you want to make products, but products are made, like if you want to take a Cartesian product, you would need ordered pairs, right? But how do we encode ordered pairs? That's what I'm saying is, so like, we have this intrinsic idea that you can make an ordered pair, which is totally fine, you can, but if we want everything to just be sets, for instance, how on earth could we use sets to represent an ordered pair? Here's a night. Someone go, yeah. Oh, you got it. Subsets, yes, let's use subsets. Exactly, let's do something like that. So here's an idea. What if AB was just shorthand for the set with A and the set with B in it? Then BA would just be the set with B and the set with A in it, which is, notice, not equal to the set with A and the set of B. Yeah? So they're distinct. Hey, that's pretty reasonable. You could just nest things, right? And as soon as you've got an ordered pair, you have ordered lists as long as you want. That is, you could take A, B, and C, and you could just define this to be the ordered pair with A and B. C as like the second one, perhaps. Whatever way you want to go about doing this, yeah? And now you've got as long of a list as you feel like. You can do infinitely long lists. Hey, kind of cool, right? But notice, you could do this in many different ways. You could have had the first coordinate be the thing that gets the subset, or you could have done like a bunch more set brackets or something like that, yeah? But what I'm trying to point out is that when we're bringing in ordered pairs, which is what we're about to do, there is no need necessarily to appeal to some new type of object. That is, we don't need to assert the existence of a brand new thing called an ordered pair. We could instead just deal strictly with the types of things we've been seeing so far and use a new notion like an ordered pair by encoding that notion, the thing we want to represent, in our set of objects that we already have. That way, we're just reasoning about things that we've already seen, and we don't need to actually expand our universe of objects we're talking about. I guess what I'm trying to point out is that sets are actually quite rich. You can encode ordering structures inside of them very well. You don't need to introduce new types of things. You can just look at subsets of the incredibly rich world of sets. Kind of nice. Cool. You could even imagine, if you think about it, now you have some sort of like lists of things with things in order, right? You can imagine numbers as lists of numerals, right? Like the number 1034 is 1034, right? You could encode that in some way, perhaps as a list of numerals, and you could encode each of the numerals 0 through 9 in sets, and then hey, all of a sudden you're able to represent all of the positive integers in sets. And now if you want to talk about positive versus negative, you could just do, well, positive has, something in the first coordinate, negative has something in the second coordinate of yet another ordered pair that you put the previous things into, right? And hey, if you want to talk about, numbers with like decimal digits, perhaps you could just make those into very, very long, potentially infinitely long, ordered lists, right? So we just maybe introduce some sort of a new, thing before the decimal place, thing after the decimal place, use yet more ordered pairs. But you can imagine just by stacking complexity on top of complexity, making a lot of ultimately kind of arbitrary choices about how you want to represent these things, that you could use sets to represent virtually any number you could conceive of. In fact, all of them, right? Maybe you could use sets to represent basically everything in mathematics. Perhaps. But gosh, we would need a big set for that. Ooh. How do we know such a set exists? Could we tell? A hard question. A good question. Something that people have been very interested in. Something that we'll talk more about later, and kind of related to the same sorts of foundational issues we saw with Russell's paradox and all of that. That is, what things are sets and what things aren't sets? How can we use comprehension in a reasonable way, perhaps not just straight up unrestricted comprehension, but some more nuanced, restricted form of it? How can we build mathematics from the ground up with as few things as possible? Perhaps sets are a good candidate. We don't even need to put anything in the sets. We could just use the empty set, or the set of the empty set, and the set of the set containing the empty set, and so on, right? You don't even need to put anything in the sets except for other sets. Maybe you could just say there's sets. Hey, who knows? We'll find out more about this later, but let's build another kind of construction using sets so we can see some of their richness. We're going to use ordered pairs here, not necessarily represented via sets, but my point from that little diversion was to say that when we introduce ordered pairs here, you should not think of them necessarily as something new, something that we haven't had before, but instead something that we can see in all the stuff we've seen before, but just under perhaps some essentially arbitrary encoding. Yeah? Maybe? No? Long monologue? How about it? Okay, definition, Cartesian product. So the Cartesian, named after Descartes, product of two sets, A and B, is the set A cross or A times B that is defined to be the set of ordered pairs A and B such that A is in A and B is in B. Okay, so this is a nice, here, by the way, AB denotes an ordered pair. This is a nice way to take two sets and to build a bigger, newer set, right? We've talked about some of the other ways you can put sets together. Here's a new way to put sets together. You get yet another set. The objects in it now are ordered pairs. We're kind of glossing over exactly how you would perhaps want to encode ordered pairs, or perhaps we're asserting that there exists a new object called an ordered pair not present in sets from before. Either way, as long as it works like an ordered pair, this will be just fine. So however we want to encode the information is essentially irrelevant, but it's a good thing to think about. So, ordered pairs, Cartesian products. So, all right, let's prove a theorem about this. And in fact, I will go through and prove this on the other side. Now, one perhaps visualization that I think is nice is that A cross B works like, if you want to think of it like this, works like works like the plane R2, even when A and B are just sets. That is, if you have A cross B, you're saying like, hey, in one coordinate I've got A's, and in the other coordinate I've got B's. Let me draw this actually slightly lower down so I have a little bit better room. Now, granted, these things are not all nicely ordered, yeah? But effectively, everything in A cross B is just like take something in A, some little a. You can kind of think of it like, hey, for everything here, you have a A and a B, yeah? Like if you just lined all of the elements up from A1 through A whatever, even if it's infinitely long, whatever, if you just line them all up, whatever ordering, there's no intrinsic ordering to A or B, but if you just line them up and you make like this little like, XY axis sort of thing, then just going and picking a point tells you an AB pair, and it works exactly like the plane. Yeah? So while it maybe feels more mysterious to just do this with sets, it's really nothing different than saying, hey, one chunk is from one set, one chunk is from the other set. It's in a sense like kind of the weakest form of like coordinatization possible. Something from one thing, something from something else. Nice. Okay. So let's go and let's prove some facts about all of this. Back to the other board, which I'll now erase. And we will prove theorem 3.16 in your notes now. If you want to start looking at that while I wipe all this off. All right, so we're going to prove theorem 3.16, or at least a little bit of it. Now, theorem, what this says is that for any sets A, B, and C, we have the following. 1, A union B cross C is equal to A cross C union B cross C. 2, A intersect B cross C is equal to A cross C intersect B cross C. Nice. And then finally, how does this interact with the relative complement, the set difference? We have A set difference B cross C. Well, this is just equal to A cross C set difference B cross C. And that's not so bad. Let's do the first part right here and see how it goes. So what would you do? How would you start this? What is it even saying? A good question to ask at the beginning of any proof. What does it mean? And just to look at my watch. Okay, good. The clock in the back of the room keeps getting progressively further and further off every week, which is weird because I'm pretty sure it's actually like wired. It's not running on batteries that are slowly dying. It's like in fact wired to the building, which doesn't make any sense why it would get further and further off every week. But, you know, got to keep me on my toes, I guess. So what does this first one say? A union B cross C. Well, it's A cross C union B cross C. Okay, so I've got, let's kind of draw the picture of it. I've got A, I've got B, then here together, this whole thing is A union B. And then if I draw my picture here of C, and I think of the blob you form by picking a thing from each one, right, as A union B cross C, if I think of this blob picture, what it's telling me is that effectively all this is taking the A piece and the C piece, and you go and you draw like the, you know, chunk of the blob that's above this, right? So this would be A cross C. And you can do exactly the same business with B. You can say, hey, here's B, and there's C yet again. And so I can take this little part of the blob above it. This would be B cross C. And now look, if I want to get A union B cross C, I just take both of those together. They might have a little bit of overlap. That's okay. Just union them together and you get the whole blob. Does that make some sense why I'm trying to say that this works basically like the plane, right? That you can take your coordinate axes sort of, and it helps you visualize what the heck is going on. Can we see the second part just as well? A intersect B cross C. That would be just grabbing, say, this little portion in here, which is A intersect B. And if we look at what that portion is, it's just right in here. This would be A intersect B cross C, since we're just essentially taking this piece and stretching it along C, taking one copy of it for each element of C. Yeah? Okay, and you can imagine taking this piece and that piece and just looking at their overlap, right? Which is exactly what the second part says. Nice, okay. The final part, totally fine. Same business too. A without B cross C. Well, A without B is just this last little chunk right here. So it's just this little chunk right there. Yeah, when you take A without B cross C. And it says take A cross C, take B cross C, and get rid of B cross C. That is, take all of A cross C, take B cross C, get rid of that little piece that overlaps, and you're just left with this. So visually, it's really easy to see. Maybe? Yeah? Seeing either smiles or a smile of, eh. Okay, if it doesn't make it easier to see it this way, that's totally fine, because we can rely on our symbolic, manipulation instead of our physical intuition. Though I see people beginning to close their bags, which reminds me that The clock is wrong, as I just said. So I'll see you next time when we'll prove this. Actually, no, I won't prove this next time, nor will I prove it the time after. I'll prove it a week from today. See ya. Bring your questions next time, and have a great day.